the actual title that I sent in. But it's something about XYZ and Painlevé. And I should say that it's joint work with Christian Hagendorf from Louvain-la-Neuve. And also this is something that somehow was very difficult to finish. It was almost finished for a long time, but I think, well, I know some of you have heard me speak about it before, then I always said that the paper will soon be on the archive. But now it's actually there, so you can see the paper for yourself. So let's see if this is working. Yeah. So this is something we discussed at breakfast, some of us. Dyson has this notion that all scientists are either frogs or birds. And in this talk, it will be like a frog's perspective. So it will be like this. I will show you some things that we found in the mud, basically, some nice things. And then I show it to you. And then maybe some of you are birds and can tell me what these things mean and what they imply or whatever. But yeah, that will not be in this talk. Okay, so the plan is I will start with the XYZ chain and then move on to Painlevé and other stuff. And I think we saw quite a lot of spin chains already, so you probably got a bit used to it, even if it's not what we're working with. So the chain I'm talking about it's a chain of length L of spin 1/2 particles, so each particle carries some two-dimensional Hilbert space. And then we have here, you see some interaction between neighbors. What we haven't seen before is that this is completely anisotropic. So there's 3 different parameters here, Jx, Jy, Jz. There are just some numbers that you could somehow fine-tune to set the interaction in different space directions. And I will only consider this with periodic boundary conditions. So it just means if you should see the index L plus 1, it really means 1. So the L particle talks to the first particle. Okay, any questions on this? So actually I will not consider this in generality, but only a special case, which I will call, for reasons that I will come in. Supersymmetric case. And it's the case when the second symmetric function of these parameters vanishes. And this might seem more familiar, I think, to some of you if we look at the special case of the XXZ spin chain. So XXZ, that means that 2 of these parameters are the same. So we might as well put Jx and Jy equal to 1. And then you can solve this and see that Jz. And this -1/2 is usually called delta. So it's the delta equal to -1/2 XYZ chain. And sometimes delta is called Q plus Q inverse over 2. And then you see that Q has to be a cubic root of unity. So that was mentioned briefly in Didina's talk, this interesting root of unity cases. And this is really very special because we have some, for these parameters we have some solvability already defined. So I mean, usually in statistical physics if we can compute some stuff well, the system gets very large, we say it's solvable. But this is much more unusual that you can write some concrete closed formulas even for finite systems. And you basically just have this under this special condition on the parameters.
Well, solvability in what sense?
Well, I mean, I will tell you in one sense that we can compute some correlation functions. Yeah, but, I mean,
sure.
Keep listening. Some physical interesting quantities can be computed. Okay, so why do I call this combinatorial? Well, at least that's really a very big story about the XXZ model with delta equal to -1/2. You might have heard about the Razumov-Stroganov, X conjecture and things like that. So there's a lot of connections to combinatorics of alternating sign matrices and plane partitions, things like this. And for the XYZ chain, there's not so much that have been done, but there's some earlier work of mine. There's some connections to 3 colorings. So some combinatorial object of this type. So I will not talk about this. I just show you the picture as some kind of teaser. Why is it called supersymmetric? Well, I mean, now I'm actually out of my comfort zone, but physicists claim or know or expect or whatever that there's some limit from this chain to some massive Sine-Gordon theory. And then this condition is supposed to be really the supersymmetric condition for this quantum field theory. But there's a much more pedestrian version of this that Painlevé and Hagendorff discovered. So there's really some supersymmetry already at a finite lattice. So you can write the Hamiltonian here as some constant times the anticommutator of some supercharge with its adjoint. So this Q is nilpotent, and it actually acts by adding a particle to the chain. So like instead of interchanging fermions and bosons, it interchanges change of even and odd length. And they just have this in a subspace, but it's a big enough subspace for well, what I will talk about at least. Okay, so it's called supersymmetric and combinatorial. So the title of this slide I borrowed from Stroganoff's paper on this, one of his first papers. So the paper is called The Importance of Being Odd, which I think is a great title. So there's something different here between change of odd and even length. But let's start with Baxter. I mean, this is very famous that in 72 Baxter solved the XYZ spin chain in the sense of commuting the free energy or the asymptotic of the lowest eigenvalue of the Hamiltonian. And his expression is not simple. I mean, it's an infinite series. But it turns out that if you have this condition, then all terms in this infinite series vanishes except the first one. So you really have a dramatic simplification. And that's something that Baxter mentions in his paper. And what happens is that the lowest eigenvalue asymptotical it's just like the sum of the anisotropy parameters. So a very simple form. But what Stroganoff noted was that this seems to hold. Okay, so this answers your question, Jesper. It's an example of this finite solvability that for change of odd length, it seemed that this holds exactly. So the lowest eigenvalue of Hamiltonian is exactly this. And this was actually proved not that long ago by Hagendorff and Leonardi using this supersymmetry I mentioned. So this constant I told you about is this E naught. So I mean, this gives some lower bound of the energy, and then they show, I mean, just using some kind of general principles that this lower bound has to be achieved for change of odd length, but not for change of even length. So it's a difference. Yeah, so again, I assume that I'm in this Stroganoff condition setting, so I have periodic boundary, I have this condition, I also have this. So I mean, if I wouldn't have this, then I would be talking about the highest energy state instead of the lowest energy state. But probably you like the lowest one better. And the chain will have odd length, so I write the length as 2n plus 1. And then the ground state is actually double. So that's basically one ground state with an even number of upspins and one with an odd number of upspins. So we will just pick one of them, it doesn't matter. And then the correlations we're interested in are these. Quite simple correlations, so it's nearest neighbor correlations. You measure the spin in some direction between two neighbors, and you assume also that the system is kind of frozen to its ground state. So you have one of these correlations in each direction, Cx, Cy, and Cz. So these are the things that we want to compute. And to show you that it's not quite unreasonable, I can show you what Stroganoff did for the XZ chain. So then, I mean, these, well, all the constants are fixed, so then they only depend on the length of the chain. And Stroganoff derived these formulas for the correlation functions. So I think you agree that well, for instance, compared to some things we saw yesterday, these are very simple formulas for correlation functions. Okay, so I want to say what these correlations are, and then this is kind of a preliminary result. So this is actually quite easy to show that. So here A is either X, Y, or Z, and you see that this A only appears here. So that's a very simple kind of thing with the eighth parameter, and then apart from that, it just depends on one function that I don't Fn. And this Fn is symmetric when you interchange the anisotropic parameters. So it's actually a function of this variable here. And you can compute some of them and you get some, well, more or less nice formulas for Fn. Okay, so to compute the correlations, I need to say what Fn is. So that's what I'm going to do. And what we will do is that we will express Fn in terms of certain polynomials introduced by Bachanov and Magasiev that are called Sn and Sn bar. So the bar doesn't mean complex conjugate or anything. It is just two different polynomials. And they have some interesting properties. They are tau functions of Painlevé 6, and they are related to the Q operator eigenvalue. And I come to that later. I can't say everything at one time. But for now, let me just say that you can define them explicitly by some recursions, which look a bit messy, but I mean, if you put it on the computer, it's quite quick actually. So if you take Sn plus 1 times Sn minus 1, then it's some quadratic expression in Sn and its first two derivatives, and well, with a bit messy coefficients. And if you then start with initial values S0 is 0 and S1 is 1, then you can iterate this actually both in the positive and negative direction. And you observe that you get polynomials all the time, which is, of course, well, if you see the recursion, it's kind of magical that you get polynomials, but you do. Okay. And Sn bar, I didn't write that, but I think for Sn bar, you just change this 5n plus 3 to 5n plus 1 or something like that. It's almost exactly the same recursion. Yeah, and here comes the main result. So for that, I need to parameterize the change somehow, and this is just a convenient parameterization of this supersymmetric case I'm looking at. And then the formula is this. So I say that this function Fn, there's one term that doesn't depend on the chain length, and then there's another term which has this S bar and S polynomials, and with both positive and negative indices. And we have, well, we try to work rigorously so we can prove this. Some technical condition. I need that. I will come to it. Okay, and one thing you can compare this with what you have for infinite chains, because that's that you can compute from Bax's formula for the free energy. So if you look at Bax's formula for the free energy, then from that you can compute. Well, you could also compute these correlations, and they also simplify this supersymmetric case. And what you get is, well, again, rational functions, a bit different here in different parameter regimes. And if you look at this first expression here, then you see it's exactly this term here. So this first term, that's actually the infinite lattice limit, and then the second term with this Painlevé stuff, that's the finite length correction, exactly. And that's actually, I told you that this function has some symmetries that are not apparent on the right-hand side. So you could apply those symmetries, and then you will get different formulas here, where you have different first terms and different second terms, and the two. The different first terms will be these things. So, you have some. In each of these three regimes, you have something that you can interpret as infinite length term. That's what I want to say. And if you're interested, this thing it has kind of third order phase transition. So the third derivative of this function jumps at the points 0, 3, and -3, which are exactly the XXZ points, the 3 points where you degenerate to the XXZ speed chain. And I have, well, I made a picture of this. I don't know how exacting it is, but you see here. I plotted this Fn for n is 2, 3, 4, which corresponds to chains, so lengths 5, 7, and 9. So they are here, and then the one on the top is this F infinity. So that's just a piecewise rational function. And you see, even for the length 9, I mean, you're just like at most 1% away from the true thing. Okay, so now I want to come to the Painlevé equation. So now, first that's the challenge. So when should I stop? Because I don't know what time I start.
You started a bit late. You should stop 3:45. So you still have 14 minutes left.
Yeah, I have lots of time. Good.
I'll remind you 5 minutes before.
Yeah, sure. Okay, so I want to say something about Painlevé's 6 equation. I mean, some of you know a lot, I'm sure, but maybe some of you haven't seen this before so much. So I will try to give some kind of general introduction to Painlevé 6. Okay, so what's Painlevé 6? Actually, you could say it just in words. What Painlevé did was that he classified all the second-order ordinary differential equations whose movable singularities are poles, and he found a list basically. And Painlevé 6 is the most general ones. Apart, I mean, there's also some kind of the general things that don't fit in this on this list, but essentially it's this. And I want to show first the elliptic form of Painlevé 6, which looks really simple. So you have here that the second derivative of some function is actually some of this q, so it's an elliptic function of q. And here I have, okay, so this is actually Weierstrass P function. And so the alphas here are parameters, and you see that the time here, that's basically the modular parameter of the P function, so one of the 2 periods that it has. And the gamma j's, they are, well, the 4 half periods. So, well, I didn't tell you how to order them, but it really doesn't matter. Okay, so that's one way to write the equation. But you could also write it another way. So I mean, here's the equation again, and you see that if I would add to q some period of this elliptic function, then the right-hand side doesn't change, and the left-hand side also doesn't change. So you could think that q is really a variable on the torus. And the torus is an elliptic curve, so you could write this in this form, which is one of the standard forms for an elliptic curve. So the S here depends on E then. I mean, classically S is called the lambda invariant, because it's denoted by lambda usually. So I mean, there's some change of variables here, so you could change the variables from this Q and T to this X and S, and then you obtain the algebraic form of analysis, which, I mean, that's typically what you see in books. That's typically how it's written. You see, I mean, it looks a little bit like the hypergeometric equation, but it's really highly non-linear. Lots of non-linear stuff in there. Was there a question? Okay, and then I want to say that there's also a Hamiltonian form of Painlevé 6, so that was, it was actually a Swedish mathematician who discovered that. But now I give you Manin's elliptic version of this, which is much simpler to understand. So, you know, of course, if you have a secondary equation, you can always write it as a system of 2 first-order equations. But the point is that you can do this really with a Hamiltonian system. So Painlevé 6 is equivalent to this system where the Hamiltonian, so you have a kinetic term and a potential. And the potential is, so it's what we had before, but now I don't have the derivative. Before I had the derivative, now we have kind of integrated that.
But you had 4 terms, you have 4 terms, and before you had 3 terms in your sum.
Did I? Yeah, that's from 0 to 3. Oh, yeah, sorry.
Sorry.
Yeah, this should also be from 0 to 3, but it's 4 times. I mean, because we have 4 half here. And this type of potential, I mean, you know, it's an non-stationary system. The potential depends on time explicitly. But this is something that, I mean, appears in many contexts. Many people call it Treibich-Verdier potential, but really, I think Darboux was the first to study that. So some people call it innocent potential and so on. It also appears in these Calogero-Sutherland models that some people have talked about. Okay, so the Painlevé 6, I mean, it's just the Hamiltonian system based on this potential. That's what it is. Okay, so now I want to say that there are some special cases of Painlevé 6 that you can solve very easily. So for instance, when all these parameters alphas are 0, then you can solve this equation easily. So just to see if you're awake, can someone tell me what the solution is?
The 0 would be 1.
Yeah, I couldn't hear what you said. But yeah, I mean, it's an easy equation, but I mean, now when you solve that, I mean, that means that you have also solved this thing when all the alphas are 0. And that doesn't seem so easy. And that's actually what Picard did. So Picard solved this equation when all the alphas are 0. So that's why they are called Picard solutions. Okay, and then the next thing is that, I mean, one nice thing about Painlevé equations is that they have a lot of symmetries. So they have infinite many symmetries. So if you have one solution, you can start acting with this solution on your symmetries, and you get infinitely many solutions. And then typically with different parameters. And using that, you could, I mean, in some principal sense, you can solve Painlevé 6 using this method whenever all the parameters are half squares. And that's called the Picard class. So in some sense, the solutions of Painlevé 6 are kind of known. Even though, I mean, if you want to do things explicitly, you get very complicated stuff, but they are known for these special parameters. Okay, so I'm trying to come to what these S and S bar really mean for Painlevé 6, and for that I need to say what tau functions are. So for me, tau function is just something that kind of generates the Hamiltonian flow over there. So you take the Hamiltonian, you plug in the solution, and then the tau function, the logarithmic derivative of that should be this Hamiltonian. And in some sense, tau functions are a more fundamental object than the actual solutions. There's some general theory telling you how you can get the solutions from the tau functions and so on. And now I can tell you at least roughly what these S and S bar are, where they can be identified with tau functions, which correspond actually to some algebraic solution in the Picard class. So not everything in the Picard class are algebraic. I mean, most of them are transcendental, but for some special choices of parameters, they become algebraic. And S and S bar are such special cases. And I will come back to talk a bit more about parameters at the end, but I just mentioned that here I have done the parameters that correspond to these S and S bar. So you can, well, you have started from the Picard class, but then you kind of, in two directions, you apply some Beckland transformation and move further and further away from where you started. Okay, so now we can address this question. I mean, now I have said that each of those things are tau functions. But what do the whole thing with product of 4 tau functions really mean for Painlevé 6? It turns out that this has a good answer, but it's a kind of a curious answer. So what this big thing is, it's really a Painlevé 6 Hamiltonian with these parameters. And into that Hamiltonian, you plug in a solution of Painlevé 6 with a very special solution, a solution with different parameters. So it's very odd. I don't know if you have seen anything like it before. I mean, I have asked people, and everyone just said it says it's an odd thing. But I mean, that's exactly what it is. I mean, what I'm saying is that the correlation function of XYZ they are distinct. They are the Painlevé 6 Hamiltonian where you plug in the solution of another instance of Painlevé 6. Okay, any questions so far? Well, now I come to I want to say something about how we prove this, and a lot of this is just messy computation, but I will try to somehow communicate the main ideas behind it. And we use, just as Stroganov does, the main thing is to use Q operator and the TQ relation. So let me say something a bit about this, or maybe remind you. So to talk about that, you need to parameterize things by elliptic functions, basically. So okay, so now this is the general case of the XYZ spin chain. So that can be parameterized by two parameters, a crossing parameter eta and a modular parameter tau. And I can write some explicit formulas with elliptic functions, but I'm not sure you want to see them. And the supersymmetric case, that's eta is pi over 3. So again, it's kind of cubic root of unity case. And this we have talked about for XXZ, so there's some transfer matrices that commute with the Hamiltonian. In this case, transfer matrices of the 8-vertex model. So they depend on eta, but also on another parameter u. And the Hamiltonian is basically contained in this commuting family. Well, if you take the derivative of this thing at some special point, which in my convention it's u equal to eta, then you get back the Hamiltonian. And then what we could do, we had this, we had this at this supersymmetric point, but we can imagine that we can extend this in eta at least a bit around this supersymmetric point. So we extend the eigenfunction and we extend the eigenvalue epsilon, and then this will also be an eigenfunction of the transfer matrix with some eigenvalue I not by little t. And of course epsilon will be the logarithmic derivative of this little t at the special point. And then what we do, well, here's the Hamiltonian again. Of course the eigenvalue, that's basically the expected value of the Hamiltonian. Again, with respect to the ground state. So if you just expand this linearly, then you get some. The expected value of each of these terms will be some correlation function. So you have just some simple expression in terms of the parameters and the correlation functions. And then this depends on eta and tau, so you could take derivatives on eta and tau. And then there's a little mathematical trick. So it's known as the Hellman-Feynman theorem. So even if those the correlations do depend on eta and tau, but you can pretend that they don't, and you get the correct result. That's what the Hellman-Feynman theorem says. So using that, then you will get a system of three equations. This one and two from the two derivatives, and you have three correlations. So you could solve that. And the solution will then be expressed in epsilon and its derivatives, and epsilon in terms was expressed in terms of derivatives of t. So at the end you get something expressed in terms of something like this, so some kind of second logarithmic derivative of t in u and eta. And here, the u derivatives are not bad, but the eta derivatives are bad because, we have this kind of finite solvability only at eta is pi over 3. As soon as we vary eta a little bit, then, we don't know anything explicitly anymore. So we want to get rid of the eta derivatives. And that's basically what the Q operators do. So a Q operator, well, that's, this comes from the work of Baxter. It's some other family of operators that should commute with your T operators and satisfy such relation that if you multiply T and Q together, you get a linear combination of two Qs with shifted parameters, shifted spectral value. And the coefficients, in this case, the coefficients are just some power of Jacobi filter functions. So if you believe that such an operator exists, then you could evaluate this at the eigenvector and get the corresponding relation between the eigenvalues of the T of the transfer matrix and the Q operator. And well, I mean, basically using this, I mean, I had something with the T. Using this relation, I can transfer that to some expression involving the Q, or the eigenvalue of the Q operator. But there's a small technical problem with this, which is maybe not so obvious. And the problem is that we need to differentiate the TQ relation at this special parameter. And typically, Q operators tend to be degenerate at these kind of special parameters. So I mean, there's different Q operators you could use. So I mean, Baxter has 2 or 3, I think, but none of them work in our setting. None of them work at this special point. But there's other constructions by, for instance, Fabricius and Rowan that work at the critical point. But I mean, that's not good enough if you want to differentiate, right? You want to somehow connect these two. And as far as we know in the literature, there's no Q operator that's really analytic in eta near this point. So that's something that seems to be missing. So what we have to assume is that this equation should have some solution which is entirely new and analytic in eta near this special point. If we assume that, then everything is rigorous. And of course, I mean, this is just the scalar equation. So I mean, this is actually weaker than the existence of the Q operator. Maybe you show this in some other way you could imagine, without writing some detail. Okay, anyway. So after some computations, so I mean, the strange thing, I mean, we needed this Q operator to have eta derivatives, but still at the end of a long computation, all these eta derivatives cancel. That's a nice thing. And you can express the correlations in terms of something like this here. So did I tell you what phi is just some theta function? I think it was not. So some bilinear expression involving the values of the Q operator. The Q operator eigenvalue at different points. And this is basically what Stroganov did for the XYZ spin chain, but in his case, he can just write down what this function Q is and compute this thing. For us, it's not that easy to compute. We still have a lot of work to do. But what we can observe is that those polynomials we are after, they also have some expression in terms of the Q operator eigenvalue, but they involve specialization at different points. For instance, this S bar polynomials, it's basically the derivative of the Q operator as a specific half period. So some of the other ones are more complicated, but somehow we need something that will move us from some special point to some other special point. And that we had some trouble with until we found so there's some kind of differential equation that this thing satisfies. That I think could be a bit interesting, maybe from other perspectives, so that's something I want to highlight. Okay, so is the Q again, this is just some normalization. I mean, in this business, theta functions are trivial, so I multiply by something trivial. And then what I claim is that so here we have something like, well, Laplace equation with a potential, so second derivative minus the potentials times psi. And the potential is again this Dibor in a sense, or whatever potential, but with some other parameters. If you evaluate this, you get a linear combination here of the function psi itself and psi shifted by some, well, some half period basically. So that's some, well, I think interesting property of the Q operator eigenvalue that we didn't know before, and it's really the key point here. I mean, actually, we had some much more complicated proof before, but this simplifies the proof. But this is all I wanted to say about the proof, really. So, I mean, apart from the things I highlighted, there's also a lot of computations going on that I don't think you... Well, if you want to see it, you have to read the paper. I'm actually... Well, I have plenty of time, so...
We still have 20 minutes left.
Yeah, I don't think I will use 20 minutes, but you will have a longer break. So I just want to conclude by mentioning something related to Mannin's paper. So this is Mannin's paper from Painlevé 6, which is actually a very nice paper, I think. And as you see, this is how he concludes this paper. So what he's saying here, so I mean, he talks about generalized Labé potential. That's just what I call Darboux potential here. And he says that, okay, they appear in theory of KdV equations. I mean, you could also say, I mean, theory of integrable models in general, theory of spin chains or whatever. They appear in many places. And he also talks about classical integral potentials of 2-2. So 2-2 is just Painlevé. And classical integral means that you can write down solutions explicitly, as I told you in the Picard class. So that's basically two cases where you can do this. So what he's saying here is that usually in an integrable system, you will see Painlevé equations where these parameters are triangular numbers. But the simple cases of Painlevé 6, where you can solve it explicitly, the parameters are either half squares or half of, well, you see what it is. A half number squared divided by half. And he asks, is there a direct connection between the two phenomena? And that's something I can't answer, but at least if you paid very much attention, you saw that actually I had all three cases here together. So you saw the half square, so I said that the correlations, they are basically I'm talking about Painlevé 6 with this type of parameters. So this is a type where you have hypergeometric solutions and things like that. But what you plug in is a solution where you have this type of parameters. So this is the Picard class, where you have also some explicit solutions, but quite different in nature. And I said, in this differential difference equation, I had this triangular number, so the co-operator eigenvalues, that satisfies an equation with triangular numbers in. And we could also mention here that Bachanov and Magasiev found this, what they call the non-stationary Lamé equation. So some people call it quantum Painlevé 6 because, I mean, well, if you think of this T as imaginary, this is like Schrödinger equation and you have the same potential as for Painlevé 6. So the Q operator eigenvalue multiplied by something nice satisfies this type of differential equation. And here the parameters also triangular numbers. So similar to those, but a little bit shifted. So I think it's curious here that all these three cases of the potential appear together, and I mean the proofs we have, I mean they don't really give a clue why this is connected. I just want to finish with some questions. What else could you do? Well, you could look at other correlations. So, I mean, 1 point correlation should be simpler than 2 points. But we actually have some. Well, we have, or my co-author has computed some 1 point correlations, and it seems it's actually also expressed in terms of not these polynomials I showed, but that kind of sibling polynomials of those. And also something that people have looked at a lot is for the XYZ spin chain, for instance, is emptiness formation probability. That's basically the probability that you see a long chain of upspins inside your chain. So it's the simplest, maybe multi-point correlation function. So those two are things that we could hope to compute. Another thing would be to look at the scaling limit to this Sine-Gordon theory, and then, well, of course, we should let the number of sites tend to infinity, but we should also let the modular parameter tend to infinity, and in some bit curious way, they have to be fine-tuned a bit. And this supersymmetric Sine-Gordon is not related to Painlevé 3. So it would be nice if you could match our results with something in this quantum field theory. I mean, that's something that we haven't looked at all. And of course, as I said or hinted already, I mean, what's really missing here is conceptual explanations for all this. So to us, I mean, the relation between the XYZ model and Painlevé sticks equation, it just falls out of massive computation. There's no conceptual understanding of why. So I mean, that's something that I think calls for some type of explanation. And another more concrete problem is, I mean, we have this special eigenvector. What is it really? So, I mean, for the XXZ model, you can actually write down explicitly what it is. For every component of this vector, you can write down some explicit integral formulas. So that was done by Rosengren and Chalmers. So, I mean, some people, including myself, have worked quite hard to try to generalize this to XYZ, but we haven't succeeded. So if someone could find some kind of closed formulas for psi, then actually I think several open conjectures in this area will follow immediately. Okay, and that was what I wanted to say, so thanks for your attention.
Thank you very much. We have plenty of time for questions.
So in the scaling limit, do you get the sine-Gordon theory at a specific coupling or as a function of the coupling?
I mean, to be honest, I don't know. I mean, I don't. Maybe Bajanov can answer because I basically picked this up from your papers.
So it will be special coupling.
Yeah, I mean, I should say, I mean, I'm a mathematician, so to me, I mean, spin chains are okay, but I mean, supersymmetric. That's a big base, right?
Alex, you had a question.
The fact that the Hamiltonian was supersymmetric in your derivation, how important was it? How useful was it?
Yeah, I mean, in some sense it's crucial because I mean that's what we need to show that this special eigenvalue exists. So that's the starting point. But after that, we don't use it at all. So I mean, we're not actually using it in our paper. We just use the existence of this eigenvalue, and that was proved. But that was proved using this supersymmetry method.
Is anything known if you would go higher rank, so Baxter by Lavin? Does it also have? Is anything known about supersymmetry or kind of?
In the elliptic case, I think not, but in the I mean, for XXZ type of things, I mean, I think there's some work there.
Yeah, there's something elementary I don't understand about this. So if you take elliptic XYZ Hamiltonian, so it depends on 3 parameters, but you can kill one of them by rescaling the Hamiltonian, so you get 2 free parameters.
Yes.
And then if you impose your supersymmetric condition, okay, you get 3 parameters with 1 condition, so you get 2 free parameters, right? Or
No, you have 3 parameters. You kill one by scaling.
Yeah,
You kill one by the supersymmetric condition. So you have one
One is
parameter.
left, this zeta.
Yeah.
okay.
So all parameters are the.
Okay, no, I thought you get 2 all Hamiltonians with this. Okay.
Maybe another question. So at odd length, the connection, this phase vertex transformation to Felder elliptic quantum groups does not work, I think, because you would want to be at the 0 weight space to really do this properly at the level of transfer matrices.
Yes.
And then, of course, I think you can. Is it true? There's this sort of story for anti-periodic even length chains as well, but probably the anti-periodicity again spoils this. So, is anything known on the dynamical side? Is there any supersymmetry or kind of nice stuff there?
Yes, I mean, this vertex space transformation, I mean, they can't mess up.
Right.
But I mean,
So we can still take this special value of the crossing parameter and see if it is nice. I don't know.
yeah. So your question is about, I mean, if you work with Felder's
Right.
parameters. I mean, that's actually, I mean, since you stand on some, I don't remember the co-authors, they have a paper on that where they exactly write down such integral formulas for that model. So then you know explicitly that there's a simple eigenvalue. You know explicitly what eigenvalue.
Okay, cool.
I can also ask a question.
Yeah.
For if you send the lengths to infinity, do you recover no results with the correlators?
Yeah, I mean, that was this question basically, and we didn't check.
You didn't check yet.
No.
So you could get it just from the Baxter's expression for the energy by taking the J derivative, or you could compare with the results of Hermann and Fyodor.
Yeah, that's a good point. Yeah. But I mean, we would like to get something also from these finite length corrections.
Mm-hmm.
I mean, so then we can't just work with Baxter's expression. But
But in the limit L to infinity, it should just
I mean, maybe it will just vanish, but then I mean, then what we have done will not be interesting at all. I mean, maybe you could hope that maybe something remains.
I don't see any further questions. We have